All right, so last time we started this section called Finding Limits Graphically and Numerically. What we focused on last time was the graphical part. And we had taken a look at this particular example. We talked about the idea of coming from the right and from the left, and how if you have a limit in general, it means that the right and the left have no jump at that location and they match. So what we're going to look at this time is how we can actually use that same idea, but do it from a tables perspective. Having multiple ways to verify things is often quite helpful, especially if you feel like that doesn't quite make sense. And if you can verify it in another way, you might be led to believe that maybe it did make sense and you just were thinking incorrectly. So what I'd like for you to do is to take your calculator and you're going to put this equation into y1. In particular, if you have one where you can actually enter it so it looks like a division fraction like that, that's great. If you don't, you can go like this by putting it in parentheses, x squared minus 9, and then there's a division button, and then x minus 3, and that will make sure that your calculator understands what's in the numerator and what's in the denominator, and not inadvertently think that the 9 is the only part of a numerator with an x is the only part of a denominator or something of that nature. So while you do that, I'm going to do that as well. Once you have that entered, if you weren't here last time, so you didn't play with the table feature, we need to get that set right now so that we can make sure that you're able to find the values that you want. So if you remember, the way that you do that is you hit the second key, and it's window. So if you hit second, and then it's actually the button that says window. Right above it, you can see what we're really choosing. We're really choosing table set. But second window, I'm sorry that I don't have a way to display this very well, but it says table setup if you've hit the right button. So everybody in the screen that says table setup, or if you're stuck, let me know so I can get you there. Okay, so the first part where it says independent needs to say ask, and the second part where it says dependent needs to say auto. And you can move those around simply by moving your cursor and pressing enter upon the right part. So the first one should say ask, the second one should say auto. Okay, everybody good with that? Okay, we talked about this before, but not everybody had calculators, so I want to make sure everybody's calculator is set up correctly. If you don't have your calculator here today and you need to make sure that it's set up correctly, come see me, go to the Success Center, they'll get you set up to go. All right, so we did something like this before. We were calculating in section 1.1 slope. Do y'all remember that? And we calculated slope. It's actually a far more detailed process than what we're about to calculate today, which is a limit. So what we're doing today is actually easier than what we did in 1.1 in terms of tables. Now, you'll notice that underneath the limit notation, it says x approaches 3, right? We need values on either side of 3, so values slightly larger than 3 and values slightly smaller than 3. Now, there's nothing super special about the values that we're going to pick except that they're convenient. So if we go slightly larger than 3, 3.1 is a good value. And if you remember from last time, we did something like 3.01 and 3.001. Getting ever closer to the value 3, but still all slightly larger. And then on the other table that you would create, you do the exact same thing, but values slightly smaller. So something like 2.9, 2.99, and 2.999. So these are kind of our go-to values. If this had said x approaches 0, let me talk about what that would look like for just a moment. If it was the limit as x approaches 0, we would need values slightly larger and slightly bigger than 0. Right? And if we were doing that and we had our x column, it would be 0.1, 0.01, and 0.001, right? Those are slightly bigger than 0. What do you think it might be for slightly smaller than 0? Yeah, the exact same values but negative. So you'd have negative 0.1, negative 0.01, and negative 0.001. So it looks a little different because there's negatives involved, but it's still the same process, something slightly smaller, so it's negative. The same types of values. We're 1/10 away, we're 1/100th away, and then we're 1/1000th away. And then you're going to use your calculator and you're going to actually plug in those values. So for our problem, it's the 3.1 and so forth. So if you hit second graph, that will put you in your table. And you can enter the values, 3.1, 3.01, 3.001, and then the negative, or not negative, 2.9 on this, 2.99, and 2.999. Okay, so what did we get for the 3.1, 3.01, 3.001? What'd you guys get? Thank you. Wonderful. And how about for the 2.9, somebody else?
5.9, 5.99, 5.99.
And the reason that this problem's so much easier, or is easier than that other problem, is because we're done. When we did the slopes, we had to then calculate the slopes using those values. You guys remember that? We're not calculating slopes here. We're just finding the actual function values. So once we get those two columns of the table, we're actually looking at going down the right-hand column, the f of x values, and we're asking ourselves, what value does it approach in both lists? Well, on the left-hand list, this looks like it's approaching what? 6, and on the right-hand list, I mean, it's not the right-hand side, but I wrote it on the right, but it's 6, and they match, right? They're the same. So we would say that this limit is equal to 6 because they both match. So it's probably worth noting, just so that we've got it written from what we did last time, that this first set of numbers that I did, this first table, is actually the limit as x approaches 3 from the right, because its value is bigger than 3. And this one right here is the limit as x approaches 3 from the left, because the values are slightly smaller than 3. And if you do those tables in reverse order, it's fine, doesn't matter at all. You're still looking at the final result of both the tables, so in either order, you'll still end up with the same answer of 6. Okay, we're going to make one very slight alteration, which can be found very quickly in your calculator, because all you're going to have to do, if you've gone through the process the way that we have talked through it, is to change y equals in your calculator so that it says plus 9 on top instead of minus 9. And then you can go right, because my function's almost matched, right? And then you can go right back into the table where you already had those values, and it will have those same 3.1, 3.01s in your table. None of that actually changes. So we'll be able to simply record the new values with that one small change. So this is one of those cases where it's not going to end up mattering, but I want you to be aware that, like, the first entry on my calculator for 3.1 says 186.1. Does anyone else say that? Okay, so that may be the actual value. Like, it's totally a possibility. But it also might be that at some point that your calculator stops reporting the decimals because they get too long. So the way that you can tell which one that is, if it's the first one that it stops at 1 or if it continues, is by just moving your cursor over to being on top of it. So if I move my cursor on top of the 186.1 in the right-hand column on my table here, it actually tells me the value at the bottom, and it really is 186.1 on this one. So that's what I'll write down. Sorry about that. And if you arrow down, you'll see that it actually is not just 1806, it's actually 1806.01. And if you arrow down again, you actually get 18,006.001. And then if we continue on down our list and move over on our page, we end up with negative 174.1. Negative 1794.01, and negative 17,994.001. Okay, so everybody's values look like that from your calculator? Anything went wrong? Okay, let me take a look and see if there's a setting that might be different. Because it's going to be hard if they're in fractions to be able to interpret what you're getting close to. Fraction type right here. Let's try to get the answers in decimal. There you go.
Okay.
All right, anybody else's calculator not giving them those decimal values? Yours isn't? Okay.
I probably did something wrong. I think.
No, it's the same thing that his was. It's not, well, you're going to need this later. I'm just going to change it right now.
Okay.
I think it depends on the way you enter it. I think if you use the line, it'll give you the fraction.
If you what?
If you use the line, like if you go to the, like where you can put it in, I think it'll
Oh.
Yeah, that's probably.
Okay, for now, let's do, for what you're going to want, you're running decimals here, so that'll at least fix it for the moment. Did you put these in?
Mm-mm.
Okay. Try again. I might have changed it, so change it. Let's see if that'll work. All right, looking in the first column, 186, 1806, 18,006, so forth, what does it appear that that's approaching as you go down this table?
1806. Oh,
Sorry, I'm hearing a couple of things, but I can't get clarity. What do we hear? What'd you say, Jeff?
I didn't look at the graphicals.
Okay, that's all right. What's it look like's happening? They are going opposite directions. Let's look at just the first column for a moment. Just looking at the 186, 1806, 18,006. What seems to be happening as it gets to...
It's getting way bigger.
It's getting way bigger, right? Like one whole digit bigger. So we would expect if we got, again, like if I put another 0 in between the 3 and the 1, it would probably give me 180,000, right? And then it would give me 1.8 million, and then I'd have 18 million. I mean, that's what would happen. It would keep getting larger by a factor of 10 every time. That's about what it looks like. And that's exactly what's happening. It's actually infinity. Okay, it's approaching infinity. And if you go down the other column, what does it look like it's doing?
Negative.
Yeah, negative infinity. Do they match? No, they don't match. So this limit does not exist. Now, let me just kind of give you a heads up as to why it's happening, because it's not like we changed much. We changed one sign. Over here, it was negative on top, and over here, it's positive on top. What's the deal? Well, if you'll remember, and we'll talk about this when we get to section 1.3, or when you watch your video, what's happening here is that numerator actually factors. And not only does it factors and it cancels with the x minus 3 in the denominator. And if you graphed this thing, because we didn't look at the graph, it would look like a line. It'd look like a line, but there'd actually be a hole in the line at x equals 3. Because you can't plug in 3, because 3 makes the denominator 0. But if you look at this one, it does not factor on top because of that addition instead of the subtraction sign. And since it doesn't, we actually end up with an asymptote at x equals 3. So on one side, it looks something like this anyway. On one side of 3, it shoots up to infinity, and on the other side of 3, it's going down to infinity, to negative infinity. So that's the difference in these two results from a numbers perspective. All right, so let's take a look at the last part. So from here on, it's the homework that's written. Okay, everything we've done so far, the graphical part from last time, this tables part from this time, that's WebAssign work. What I'm about to enter into talking with you about is about what your homework that's written will look like. And we're going to consider a function that's just a line, right? F of x equals 5x plus 2. And we're going to consider finding the limit as x approaches 3 of 5x plus 2. From section 1.3, we know that this limit equals 17. We did this problem before, okay? Or we could do it in that way. We didn't do it yet. We will do it later. I'll get there. Although intuitively this makes sense to us, the description is imprecise. and we're going to consider the graph. So let me show you what that's talking about. Let's take a look. You can graph it if you wish, or you can just rely on my graph of it. You know that this is a graph of a line because it's in the form of a line, y equal mx plus b. It says 5x plus 2, so it's a very steep line, and it's crossing the axis at 2. So we're going to call this 2 right here. And what we want to know is what happens over here at x equals 2, 3. Now, the reality is, let me do it this way. If I were to go up on this value, it's a line. Lines don't have any jumps or gaps or anything in them. And there's a point right here. And this point right here is actually at a height of, can you guess what it might be? 17. It's exactly where it's at. Okay? So this is sort of the setup of this problem. As I go from the left-hand side, I get close to 17. As I go from the right-hand side, I get close to that y value of 17. There's no jumps, there's no holes, there's no nothing interesting. It's not interesting even. It's a line. Lines are boring. Okay? Well, the idea is that if I were to narrowly focus around this value of 17, right, if I were really close to 17, it would force me to be really close to 3, and vice versa, right? If the limit actually works, I'd have to be nearby that value, because that's what a limit is. A limit is saying if I get really close to x equals 3, I got to be really close to y equals 17 here. Otherwise, it wouldn't be the limit. All right, if I get really close to the McDonald's on Kickapoo, my husband gets really close to the McDonald's on Harrison, there's a problem, right? It didn't work like that. But it has to work this way if it actually are approaching the same place. And by the way, we did go to Qdoba on Monday. Just throw that in there. So the idea is that we could get really close to, in one location, we would be really close in the other. And I'm not sure if I'm going to have it drawn quite exactly right, but let me give you the image that I'm supposed to be drawing in here. That's pretty believable, right? Is that there's this sort of a neighborhood, this area around it that's got to be pretty close. So since that's the case, let's say that we want to make sure that the function value and the limit of the function as x approaches 3 are really close to one another, maybe only differing by 1 unit, okay? So they're only 1 unit apart. Perhaps we only want the 17 to go between 16 and 18. So this sort of distance away would be a 16 down here and an 18 up here. It's just 1 unit away on either side. It's not very far, right? It's real close. The question is, how close would I have to be near 3 to make that happen? I mean, can I really go from 2 to 4? Is it just a 1-to-1 kind of a thing? Or is there something else that's going on? Is there some other, like, closer area that I need to be inside of? And what we can actually do is we can actually set up an inequality to solve that question. So in particular, if I want my function, 5x minus 2, that plus 2, that graph, to be really close to 17, we don't want them any further apart than 1 away, right? I want to go between 16 and 18, right? Then I can set up this inequality. And so let's actually take a look at how this would work if I were to solve this inequality. So first of all, I simplify what's on the inside. So this is 5x minus 15, right, is less than 1. 5 and 15 have a factor in common, namely a 5. So I can factor it out. And you can actually think of it like this. I'm taking a 5 out, and then this would be x minus 3. But what's the absolute value of 5? Yeah, it's 5. So it's just 5 out here in front, x minus 3. I still have that less than 1 on the right. And I could divide so that I don't have anything but the absolute value still on the left-hand side by that value 5. So just a little bit of algebra. And I end up with 1/5. So what that's telling me is I need to be within 1/5 of each side of 3. So over here, like truly in this problem, what I'm saying is that I can only go 1/5 bigger, 3 and 1/5, and 1/5 smaller, which would be 2 and 4/5. That's how close I'd have to be on my x-axis to ensure that I'd be only within 1 away on my y-axis. That's how close. So over here, that 3x, the x minus 3 would have to be actually less than or equal, or less than 1/5. But there's absolutely nothing special about the number 1. We arbitrarily chose it. I said, let's just pick 1. What if I'd picked 1/2? What if I'd picked 0.3? We could pick whatever. There's nothing special at all about it. It's supposed to be close, right? So I can't pick 100, right? I can't go far away and ensure that this is really going to work. But in a nearby place, it has to work if there's really going to be a limit. So we can actually do this in general by using the value of epsilon. Okay, so epsilon's Greek letter, and it just means it's a small positive number. That's all it means for us. You see the letter epsilon, you know that that means a small positive number. So in order for us to find where 5x plus 2 minus 17 is less than epsilon, we would solve it in exactly the same way as we did when it was less than 1. We'd factor out the 5. We'd be left with x minus 3 for factoring. And we would divide by 5, and we would have that the absolute value of x minus 3 is less than epsilon over 5. Right? The computation is exactly the same. There's just an epsilon in place of the 1. We give this epsilon over 5 the name delta. Another small number bigger than 1. That's what delta is. Delta and epsilon are both small values, not bigger than 1, bigger than 0. Positive is what I meant to say. Small positive values, epsilon and delta. Okay, so where am I leading with this? Well, I'm leading you to be able to do the last 2 problems, which sound really scary, but they're just a little bit of algebra and then rewording of a definition with your problem. That's all they are. Okay, so let's take a look at an example with the definition first. The precise definition of limit. I gave you a really vague definition of limit that says it's the y value that you get really, really close to. That's a vague definition. It's a conceptual idea. Precisely, let f be a function defined on an open interval containing c, but except possibly at c itself. That was my 3. It's defined there, right? There's no gaps. There's no, I shouldn't say gaps. There's no jumps. I don't have any, like big spaces that are missing. Let L be a real number that the function is approaching. That was my 17 in my picture. Then for every epsilon greater than 0, okay, so epsilon was the distance that was surrounding 17. For every little distance I can pick surrounding 17, I can find a corresponding distance surrounding the 3, close enough that will be in that area. That's all this says. Such that if the 0 is less than the absolute value of x minus a is less than delta, then f of x minus L is less than epsilon. This isn't on your quiz. I don't need you to memorize this or anything like this. You're just going to be working problems with this definition. I'm going to show you how. All right, so I am going to tell you what the limit is for each of these. If you're not told, then you have to look at a graph to figure it out or at a table. So this says to find the limit L, but I'm telling you that the limit's -4. And then use the epsilon-delta proof or definition to prove that the limit is L. Okay, so in your book, I cannot remember or not, but if it doesn't actually tell you that this is -4, and I think it doesn't, then it means you find this out with a graph or table, which is exactly what the rest of this lesson has been about, using a graph or a table to figure that out, okay? So right now, I want to focus on the epsilon-delta part, so I'm giving it to you. So we're going to say it's -4. So what do? Well, it always works the same way. We start with algebra. We take that 3x plus 2, and we subtract the limit value. In this case, it's -4, and it's less than epsilon. And then this part right here underneath here, where it tells you what the limit x approaches, that's actually your goal. Your goal is to take that x value, and it'll be the opposite sign of this, and to create whatever's here to eventually say x plus 2 is less than something. That's where we're headed. When we get to x plus 2 is less than something, we've accomplished our goal. Okay, the something is a constant number. So constant meaning the epsilon will be in it because that's a constant number too. We just don't know what it is. So we just do some algebra. We just say, okay, well, this is 3x plus 2 minus negative 4, so that's 3x what?
Plus 6.
Plus 6. You betcha. We say 3x plus 6. Do they have anything in common? And they do. It's a 3. What if it had been a negative 3? Totally be fine because the absolute value of negative 3 is 3, and we would have pulled it out like it were positive. It wouldn't actually affect things like that in a bad way. I would get x plus 2 here, right? Do you see that x plus 2 that my goal was? It's there now. That will always happen. Always. If it doesn't, you've made a mistake, and it's time to go figure out where that mistake happened, okay? And then I will divide by my 3. So x plus 2 is less than epsilon over 3. This is half of the problem. Half of the problem is just algebra with an inequality and absolute values, okay? What's the other half of the problem? The other half of the problem is going back to this definition and rewriting it with your problem. So what does it look like? Well, it's going to look something like this. We know that the limit as x approaches 2 of 3x plus 2 equals negative 4. That's what we're trying to prove. Like, we know it's true. Why? Well, because for every epsilon greater than 0, that doesn't look like a 0, greater than 0, there exists delta equal to epsilon over 3 because we just found it. This is delta. For every epsilon, we started with epsilon, I found a delta such that when the absolute value of x plus 2 is less than that delta or epsilon over 3, I don't care which one you write there, then the 3x plus 2 minus my negative 4 is less than epsilon. And it absolutely always looks like that. Okay, I have one more example. It is slightly different because if you take a look at this example, it's got a square in it, right? And the last one just was a line, it was linear. So what I'm going to do is I'm going to stop the video right now because we all got to go to chapel, at least I have to. So we're going to go to chapel. I will record a video of just number 5. So if you want to go in and you can watch that, just that one little bit, it'll probably be 5 or 7 minutes, something like that, so that you can finish up the assignment. Success Center is really good with this. They'll be great. Or come and see me in my office. My office hours will be the same tomorrow. Today my office hours are canceled because I have a meeting to go to during that 1 o'clock hour. That's not normally the case, okay? But I'll be there tomorrow.